Far below the blue clouds of a planet at the edge of the Sun's family, in a darkness no light has ever reached, it is raining diamonds. Not as a figure of speech. The pressure there is millions of times greater than the air around you, enough to tear methane apart and squeeze its carbon into crystal, so that gems form high in the planet and drift slowly down toward a core hotter than you can imagine. This same hidden interior drives winds faster than sound, builds storms wider than the Earth, and powers a world that should, by every rule we know, be frozen and still. And we have seen it up close only once, for a few hours, a very long time ago. So what is a planet really doing when it makes its own heat, its own storms and its own diamonds, far from any help from the sun? Get cozy and settle in. Subscribe if you have not already, and stay with us tonight, because the engine that runs this planet is buried where no spacecraft will ever go, and we're about to go all the way down into it. Let's dive in. Part 1. The Planet. We calculated before we saw it. There is a world at the edge of our solar system that existed on paper before anyone had ever laid eyes on it. It was not found by a lucky sweep of the night sky, and it was not stumbled upon by an astronomer who happened to point a telescope in the right direction. It was predicted. Someone sat down with pencil and paper, did the arithmetic, and announced that a planet must be sitting at a particular spot in the darkness, and when another astronomer finally looked, the planet was there, almost exactly where the numbers said it would be. That world is Neptune, and tonight we are going to spend a long, slow evening with it. Because of everything in the Sun's family, Neptune may be the one we understand the least, the one that has surprised us the most, and the one that is, even now, doing something we cannot explain. To understand how strange Neptune's arrival into human knowledge really was, you have to go back to the 1840s. By then, astronomers had been watching the planet Uranus for decades, carefully recording its slow march across the sky. Uranus had its own remarkable story, having been the first planet discovered with a telescope rather than known since ancient times. But that is a story for another night. The thing that mattered, the thing that began to nag at the people tracking it, was that Uranus would not behave. Its orbit kept drifting away from where the laws of motion said it should be. The mathematics of Isaac Newton had by then been tested against the heavens for more than a century, and those laws had never failed. The planets moved like clockwork, and the clockwork could be calculated. And yet here was Uranus, quietly wandering off its predicted path, as though something out in the dark were reaching out and tugging on it. There were really only two possibilities, and both of them were enormous. Either Newton's laws, the bedrock of physics, broke down at the cold outer reaches of the solar system, or there was another planet out there, unseen, whose gravity was pulling Uranus off course. A French mathematician named Urbain Le Verrier decided to assume the laws were right, and the planet was real. He took the wobble in Uranus's orbit and worked the problem backward. Instead of using a known planet to predict where it would go, he used the deviations of a known planet to predict where an unknown one must be hiding. It was an extraordinary act of confidence in numbers, a bet that the universe was so orderly that you could find a planet you had never seen simply by trusting the equations. Le Verrier finished his calculation and sent it to an astronomer named Johann Galle at the Berlin Observatory, along with the coordinates where the missing planet should be found. On the night of the 23rd of September, 1846, Galle, with the help of a young assistant named Heinrich d'Arrest, turned the observatory's telescope to the patch of sky Le Verrier had specified. They found Neptune within an hour. It was sitting less than 1 degree from the position the mathematics had demanded, a gap so small it is roughly the width of your smallest finger held at arm's length against the sky. A planet, an entire world 4 times wider than Earth, had been conjured out of pencil marks and then located on the first night anyone bothered to look. It is worth pausing on just how unlikely that success really was, because it could so easily have gone the other way. Le Verrier was not the only person doing this arithmetic. Across the Channel in England, a young mathematician named John Couch Adams had been working the very same problem at almost the same time, grinding through the irregularities in Uranus's orbit to predict where the hidden planet must lie. He had arrived at broadly similar conclusions and arguably a little earlier, but his work was not acted upon with the same urgency, passed between busy astronomers who never quite got around to mounting a serious search. So the planet that two people had calculated independently was finally found because one observatory, handed one set of coordinates by one insistent mathematician, pointed one telescope at one patch of sky, and got lucky on the very first night. History remembers the triumph. It tends to forget how close it came to being a near miss, a prediction left sitting in a drawer while the planet waited, unseen, exactly where the numbers said it would be. And there is a deeper irony folded into the discovery, one that only became clear much later. The orbital calculations that pointed to Neptune were, in some of their details, fortunate rather than flawless. The mathematicians had made assumptions about the missing planet's distance and mass that did not perfectly match the real Neptune, and yet the prediction still landed close enough to find it. In other words, the universe handed us a correct answer partly by chance, rewarding our confidence in the laws of motion even where our specific numbers were off. That is a fitting beginning for a world that has been confounding our expectations ever since. From its very first night in our catalogues, Neptune has had a way of being found and yet not quite understood, of confirming our theories while quietly hiding the details that would matter most. We saw exactly where it was. We had almost no idea what it was. It is hard even now to hold the scale of this world in your mind. Neptune is about 4 times wider than Earth, large enough that you could line up nearly 4 Earths across its face, and large enough by volume that more than 50 planets like ours could fit inside it. It is denser than the gas giants Jupiter and Saturn, packing more mass into less space, which is part of why it earns the label ice giant rather than gas giant. A day on Neptune, a single rotation, takes only about 16 hours, which means that despite its enormous size, it spins faster than Earth does, whirling that supersonic atmosphere around in less time than you might spend asleep. And its year, a single trip around the Sun, lasts about 165 of our years. That last number has a quietly staggering consequence. Neptune was discovered in 1846. Because it takes about 165 years to circle the Sun, the planet did not complete a single full orbit, as measured from the moment of its discovery until the year 2011. Think about that. From the night Johann Galle first laid eyes on it, through the invention of the automobile, the airplane, the radio, the television, 2 world wars, the splitting of the atom, the entire space age, the moon landings, and the rise of the internet, Neptune was still finishing its very first lap around the Sun since humans knew it existed. An entire era of human history, all our triumphs and catastrophes, fit inside one Neptunian year. The planet is so far out, and moves so slowly through its enormous orbit, that our whole relationship with it has spanned barely more than one of its years. We are to Neptune the briefest of acquaintances. Think about what that meant for the people alive at the time. A planet had been calculated into existence. Nothing quite like it had ever happened before in the history of science, and nothing quite like it has happened since. It was a moment when the universe seemed to reveal itself as something almost obedient, a system so lawful and so predictable that a human being could derive the existence of a hidden world from a few stubborn irregularities in the motion of another. This is the founding paradox of Neptune, and it is worth holding on to as we go, because it sets a trap that the planet has been springing on us ever since. We calculated Neptune before we ever saw it, and that early triumph made it feel as though we understood it. We did not. Finding out where a thing is, it turns out, is almost nothing like understanding what it is. For all the glory of its discovery, Neptune then settled back into being little more than a dot. Through the telescopes of the 19th and 20th centuries, it was a small blue-green smudge, a smear of colour against the black, far too distant for anyone to make out clouds or storms or rings or moons in any real detail. Astronomers learned its orbit, estimated its size, caught the largest of its moons, and measured the colour of its light, but the planet itself stayed almost featureless. It was a name and a number and a faint blue point, orbiting so far out that it took the better part of 2 human lifetimes to complete a single circuit of the Sun. That distance is the second thing to hold on to tonight, because it explains almost everything that follows. Neptune orbits at an average of about 4.5 billion kilometres from the Sun. To put that in language the mind can actually hold, astronomers measure distances in the solar system using the gap between the Earth and the Sun, which they call 1 astronomical unit. Neptune sits at 30 astronomical units. It is 30 times farther from the Sun than we are. The sunlight that reaches it is roughly 1,000 times weaker than the sunlight that warms your skin on a summer afternoon. From the surface of Neptune, if it had a surface, the Sun would not be the great golden disk we know. It would be a brilliant star, far too bright to look at, but a star all the same, casting a pale and frozen sort of day. At that distance, Neptune is not just hard to see, it is brutally hard to reach. A spacecraft launched from Earth, even one flung outward at the tremendous speeds we can manage today, needs somewhere in the region of 12 to 13 years simply to make the crossing. And there is a further complication, a quirk of celestial mechanics that turns out to matter enormously. The outer planets only line up in the right arrangement for a single spacecraft to visit several of them in one journey, once every 175 years or so. Miss that alignment, and a mission to Neptune becomes a slow, lonely, dedicated voyage to one world and nothing else. So for almost the entire span of human history, Neptune remained exactly what it had been on the night it was discovered. It was a prediction confirmed, a triumph of mathematics, a blue point of light at the edge of everything we could reach. We knew where it was. We had known where it was with astonishing precision since before there were photographs or automobiles or electric light in most homes, and yet we had never truly seen it. We had never watched its weather, never traced its rings, never met its moons. The planet we had summoned out of equations was still, in every way that counted, a stranger. All of that was about to change in a single afternoon, when a small spacecraft that had already crossed the entire solar system finally arrived and showed us that the quiet blue dot we thought we had figured out was nothing of the kind. Part 2, the only time we ever visited. For a planet we located so confidently and so early, it is almost unbelievable how little we have actually seen of Neptune up close. In all of human history, across all of our probes and telescopes and decades of effort, a spacecraft has flown close to Neptune exactly one time. Not one time per decade, not one time per generation, one time total. And it happened on the 25th of August 1989, when a spacecraft named Voyager 2 swept past the planet after a journey of 12 years and several billion kilometers. Voyager 2 was never built to be a Neptune mission. It was launched in 1977 to take advantage of that rare alignment of the outer planets, the one that comes around roughly every 175 years. The idea was staggering in its ambition. A single spacecraft would visit Jupiter, then use Jupiter's gravity to swing onward to Saturn, then to Uranus, and finally to Neptune, each giant planet bending its path and flinging it deeper toward the edge of the solar system. It was a cosmic game of catch, played across decades and billions of kilometers, and it worked. By the time Voyager 2 reached Neptune, it had already crossed more of the solar system than any object humanity had ever built, and it was running on a fraction of the computing power you carry in your pocket today. When it finally arrived, Voyager 2 did not slow down and settle into orbit. It could not. It was moving far too fast, and it had no way to stop. Instead, it threaded the needle, passing within about 5,000 kilometers of Neptune's North Pole. That was the closest approach to any planet during the entire Voyager mission, a deliberate, daring dive over the top of the world. For a few short hours, after 12 years of silence and darkness, the spacecraft's cameras and instruments drank in everything they could, and then it was past, already falling away into the black on the far side, never to return. Imagine, for a moment, what those hours were like for the people waiting back on Earth. Neptune is so far away that radio signals travelling at the speed of light, the fastest thing there is, take more than 4 hours to cross the distance one way. So everything Voyager 2 did at Neptune, it did alone. By the time the first images of the closest approach reached the control room, the spacecraft had already finished the encounter and was long past the planet. The engineers and scientists were not watching events as they happened. They were watching the past arrive, 4 hours late, pixel by pixel, as a world that no human eye had ever resolved slowly assembled itself on their screens. A blue dot that had been a blue dot for 143 years was, at last, becoming a place. Consider what Voyager 2 had already survived to reach that moment. It had been launched in 1977, the same year that back on Earth, home computers were a curiosity and most people had never heard the word Internet. The spacecraft's onboard computers carried a tiny fraction of the memory in the cheapest phone you can buy today, and yet they had guided it flawlessly across more than a decade and several billion kilometers, past Jupiter, past Saturn, past Uranus, each encounter bending its path and stealing a little of each planet's motion to hurl it onward. By the time it reached Neptune, the instructions for the entire encounter had to be loaded in advance, and executed automatically, because the 4-hour signal delay meant no one on Earth could steer it in real time. If something went wrong during those crucial hours, the people who had spent their careers on the mission would not even know until it was far too late to fix, and nothing went wrong. The little spacecraft performed its choreography perfectly, swinging over the North Pole, turning its cameras and instruments toward the planet and its moons, gathering in the data, and then beginning the long fall away into the dark beyond the planets. The images that came back were not merely scientifically valuable, they were the last time Voyager 2 would ever meet a new planet. After Neptune, there was nothing else in its path, only the immense emptiness between the stars. In a real sense, the planet became the spacecraft's farewell to the solar system, the final world it would ever introduce us to before crossing out into interstellar space. The pictures had a kind of weight because of that, a sense of a door closing. Humanity's grandest tour of the outer planets ended here, at the most distant of them, with a few hours of frantic data gathering above an alien blue world, and then silence, and then the long drift outward that continues to this day. What that single visit gave us was a foundation, and it is worth appreciating how much we learned in those few hours, precisely because it is so much less than we would want. Voyager confirmed Neptune's size and mass, measured the makeup of its atmosphere, clocked those impossible winds, photographed the great dark spot, mapped the rings, and discovered 6 new moons in one pass, including small shepherd moons whose gravity helped sculpt the rings, and the irregular lumpy moon Proteus. It measured the planet's strange magnetic field and found it tilted and offset. It flew onto Triton and revealed the geysers and the frozen nitrogen plains. Nearly everything in every textbook diagram of the Neptune system, every labelled ring and named moon and described storm, traces back to that one encounter. An entire world's worth of knowledge, gathered in an afternoon, and then never updated from up close again. And that is exactly why the visit casts such a long shadow over everything we're talking about tonight. A foundation built from a single moment is a foundation that quietly ages. The winds Voyager measured, the storm it photographed, the temperatures it recorded, all of it was a snapshot of how Neptune happened to be in 1989, and we have spent the decades since treating that snapshot as though it were a permanent description. The planet, as we are about to see again and again, had other plans. It kept moving. It kept changing. And the first crack in our confidence, the first sign that the snapshot was already misleading us, was right there in the very data Voyager sent home, in the speed of the wind racing across the cloud tops. That number, when the scientists worked it out, was not just surprising. By every rule we understood, it should not have been possible at all. And what a place it turned out to be. The Neptune that emerged in those images was not the silent, frozen, featureless marble that distance had let everyone imagine. It was a living, churning, violent world, painted in the most arresting blue anyone had ever seen on a planet, streaked with bright white clouds and marked by an enormous dark storm. The colour alone was a revelation. Neptune's atmosphere is made of roughly 80% hydrogen, with most of the rest being helium, and a small but crucial trace of methane, somewhere around 1 to 2%. That methane is the painter. It absorbs the red part of sunlight and scatters the blue, and so the whole planet glows in that astonishing sapphire blue, far more vivid than anything its chemistry alone would seem to promise. But the colour was only the beginning. As the instruments studied the atmosphere, they began to measure the winds, and the numbers that came back did not make sense. They still do not entirely make sense. We will come back to those winds in a moment, because they are one of the first great clues that Neptune is doing something its distance from the Sun says it should not be able to do. For now, hold on to the scene itself. Hold on to the fact that everything we know in fine detail about Neptune's weather, its rings, its family of moons, very nearly all of it, comes from those few hours in 1989. One glance, one angle, one moment in time. That is a strange and slightly unsettling thing to sit with. We have an entire world out there, the size of which could swallow more than 50 Earths, and our best close-up portrait of it is a single afternoon's work from a spacecraft that is now older than most of the people alive today. Voyager 2 itself is still out there, by the way, travelling silently into interstellar space, its instruments slowly going quiet as its power fades. But Neptune, the planet it visited, has not waited for us. It has gone on turning, storming, glowing, and changing decade after decade with no one watching closely. We took one photograph of a stranger, and then we looked away for more than 30 years. It is easy to assume that one good look is enough, that a planet is a fixed and permanent thing, that whatever Voyager saw in 1989 must still be true today. That assumption, as we are going to discover, is wrong. Neptune is not a portrait. It is a process. And the single most important idea in everything that follows tonight is this. When we finally built an instrument good enough to look again, a new kind of eye that could see Neptune in ways Voyager never could, the planet did not simply confirm what we already knew. It showed us things the old picture could not contain, and it caught the world in the middle of changing into something new. But before we get to that, we have to talk about the winds, because the very first thing Voyager measured, the speed of the air tearing across the cloud tops, was already impossible. Part 3. The winds that blow the wrong way. When Voyager 2 measured the winds at Neptune, it found the fastest winds ever recorded anywhere in the solar system. Near the equator, the air was moving at roughly 2,100 kilometers per hour. That is close to the speed of sound. To put that in terms you can feel, the most powerful hurricanes on Earth, the kind that flatten cities and rewrite coastlines, top out at a little over 300 kilometers per hour. Neptune's everyday winds are about 7 times faster than the worst storm our planet has ever produced, and around the edges of its great dark storm the winds were clocked even higher, at up to 2,400 kilometers per hour. These are not gusts. This is the steady, sustained state of the air on Neptune, a permanent supersonic gale wrapped around an entire world. Now here is where it stops being merely impressive and starts being genuinely strange. On Earth, the engine that drives our weather is the sun. Sunlight heats the ground and the oceans, warm air rises, cool air sinks, the planet spins beneath it all, and the result is wind and storms. The more sunlight a place receives, the more energy is available to stir the atmosphere. Neptune receives about 1,000 times less sunlight than Earth does. By every intuition we have, it should be a calm, sluggish, half-frozen world, its thin trace of warmth far too feeble to push the air around with any real force. Instead, it drives the most violent winds of any planet we know. The amount of energy available from the distant sun is almost nothing, and yet the atmosphere behaves as though it were being whipped by a furnace, and then there is the direction. This is the detail that should make the back of your neck prickle a little. On most of the worlds we know, including Earth, the broad pattern of the winds tends to run in the same direction the planet rotates, dragged along by the spinning body beneath them. On Neptune, the majority of the winds do the opposite. Neptune spins one way, and its atmosphere tears across it in the other direction. The planet turns beneath a sky that is moving against it, a world and its air locked in a permanent disagreement about which way is forward. The reasons for this, after all these years, are still not fully understood. We can describe it, we can measure it, we cannot yet fully explain it. It is worth understanding how we even know the winds blow backward, because it reveals a subtle puzzle hidden inside the question. You cannot simply watch the air move and read off its speed, because to say how fast the wind is blowing, you first have to know how fast the planet itself is turning underneath it. On a rocky world like Earth, that is easy. The ground is solid, and you can mark a mountain or a coastline and time how long it takes to come back around. Neptune has no solid surface to mark, so how do you measure the spin of a planet that is nothing but fluid all the way down? The answer is clever. Far inside Neptune, that exotic conductive interior generates a magnetic field, and the field is locked to the interior of the planet, turning with it. As Neptune rotates, the field sweeps around and produces a faint, regular radio signal, a kind of ticking pulse that Voyager could detect. By timing that pulse, scientists could measure the true rotation of Neptune's interior, the planet's real day, independent of the clouds. Once they knew the true spin of the planet, they could compare it to the motion of the cloud features they tracked in Voyager's images, timing how the bright methane clouds and dark storms drifted across the face of the world. And that comparison is what revealed the strangeness. The clouds were not merely lagging behind the planet's rotation, as friction might cause. Across most of the planet they were moving the other way entirely, sliding backward relative to the interior turning beneath them. The sky and the body of the planet were in disagreement, the atmosphere racing one way while the world it wrapped turned the other. It is one thing to measure a fast wind. It is another to realize that the wind is running against the very planet that holds it, and that no one can yet say exactly why. Let me try to put you there, because the numbers alone do not do it justice. Imagine just for a moment that you could stand somewhere in Neptune's upper atmosphere, suspended above the cloud tops, looking out across that endless blue. You cannot, of course. There is no surface to stand on. The cold would kill you instantly. The pressure deeper down would crush you, and there is nothing solid to hold. But imagine it anyway, the way you might imagine standing on the deck of a ship in a storm. The first thing you would notice is the silence of the light. The sun hangs in the black sky, fierce and small, a brilliant point rather than a disk, and the day it casts is pale and blue and cold, like moonlight that has forgotten how to be warm. Below you the clouds stretch to a horizon that curves away faster than it does on Earth, because for all its size this world is wrapped tight. And then you would feel the wind, not as a breeze, not as a gust, but as a wall. The air is moving past you faster than a jet airliner flies, faster than sound itself can travel, a continuous screaming supersonic river of hydrogen and helium and methane. White clouds of frozen methane race overhead like torn banners, crossing the whole sky in what feels like minutes. And if you watched carefully, if you fixed your eye on the slow turning of the planet below and compared it to the headlong rush of the air above, you would realize that the whole sky is moving the wrong way, sliding backward against the spin of the world. There is no storm front here, no calm before or after. The gale is the climate. It does not pass. It simply is, and it has been screaming across this planet against its own rotation for longer than there have been eyes to see it. There is a strange and counterintuitive idea that some scientists have offered to help explain how Neptune can run such ferocious winds on such a meagre energy budget, and it is worth understanding because it flips our usual logic on its head. On Earth, friction is constantly slowing our winds down. Air rubs against mountains and forests and oceans and against itself, and a great deal of the sun's energy that goes into our weather is spent simply fighting that drag. Neptune has no surface for the wind to rub against. There are no continents, no mountain ranges, nothing solid for thousands of kilometers down. The atmosphere flows over deeper layers of fluid with very little to resist it. So one possibility is that Neptune's winds are so fast precisely because so little is holding them back. A small, steady push from the planet's internal heat, applied over countless years to an atmosphere that almost never loses energy to friction, could build up speeds that would be impossible on a world cluttered with solid ground. The winds are not fast because the planet is energetic. They may be fast because the planet is smooth and patient and has had a very long time. That idea remains debated, and it does not fully solve the riddle of why the winds run backward against the spin, but it points to something important about how alien Neptune really is as a place. We carry an instinct, formed entirely on the surface of a small rocky planet, that wind is a fierce and temporary thing, that storms blow up and die down, that calm is the natural state and violence the exception. On Neptune, none of that holds. The violence is the baseline. The supersonic backward-running wind is simply what the sky does, all the time, everywhere, with no beginning and no foreseeable end. And riding within that permanent gale, Voyager found a single feature so large and so dark that it became, for a while, the symbol of the entire planet. What makes this so important, and what makes it the perfect first clue to Neptune's deepest secret, is the contradiction at its core. A world starved of sunlight should be quiet. This one is the most violently active planet in the Sun's family. That contradiction can only be resolved one way. If the energy driving these winds is not coming from above, from the distant and feeble sun, then it must be coming from somewhere else. It must be coming from below. Something inside Neptune is generating the power to run this engine, and that hidden internal source is one of the threads we are going to keep pulling on all night, because it leads to one of the strangest interiors anywhere in the solar system. But Voyager did not only find fast winds, it found a single, enormous feature riding within them. A storm so large and so dramatic that it became the symbol of the entire encounter. It was a dark oval void in the blue, an anticyclone wider than our entire planet, and the team that found it gave it a name that has stuck ever since. They called it the Great Dark Spot. One of the scientists who studied it, the planetary astronomer Heidi Hammel, described it as one of the most dramatic weather systems ever observed anywhere in the solar system. It was the face of Neptune, the feature on every diagram and every poster, the thing schoolchildren learned to recognize. There was only one problem with making it the symbol of Neptune. By the time anyone got a chance to look again, it was already gone. Part 4. The Storm That Vanished. For 5 years after Voyager's flyby, the Great Dark Spot was Neptune. It was the planet's signature, an Earth-sized bruise in the blue, and it was reasonable to assume it had been there for a long time, and would be there for a long time to come. After all, the most famous storm in the solar system, Jupiter's Great Red Spot, has been raging for at least several centuries. Astronomers have been watching that one swirl for so long that the people who first recorded it were using telescopes barely better than toys by modern standards. Storms on the giant planets, the thinking went, are not like storms on Earth. They are not passing weather. They are near-permanent features, vortices that can outlive the humans who name them. So when scientists finally got the chance to turn a powerful instrument back toward Neptune, they expected to find the Great Dark Spot exactly where Voyager had left it. In 1994, the Hubble Space Telescope, orbiting high above the blurring effects of Earth's atmosphere, took a careful look at Neptune. The Great Dark Spot was gone. Completely. No trace of it remained. The Earth-sized storm that had been the defining feature of the planet just 5 years earlier had simply vanished, leaving behind a smooth, unmarked stretch of blue where it used to be. It had not drifted to another part of the planet. It had not shrunk into a smaller version of itself. It had dissolved entirely, as though it had never existed at all. To feel how disorienting this was, picture the equivalent on Earth. Imagine if a hurricane the size of an entire continent had been hanging over the Atlantic Ocean, photographed and studied and printed in every textbook, the defining feature of the planet's weather, and then 5 years later you looked again, and not only was the hurricane gone, but there was no sign it had ever been there. No scar, no remnant, nothing but calm open water where a storm wider than a world had churned. You would not simply update your weather map. You would have to rethink what storms even are, how they live and die, what holds them together and what tears them apart. That is roughly the conceptual jolt that Neptune delivered when the Great Dark Spot vanished. The most stable-seeming thing about the planet turned out to be temporary, and our confident assumptions about how giant planet storms behave had to be quietly set aside. What makes these dark vortices especially beautiful and especially eerie is that they often travel with companions. The dark spot itself is a region where the atmosphere has sunk and cleared, a kind of hole in the cloud deck, and around and above it, bright white clouds of methane ice frequently form, like a halo of cotton riding above a dark eye. Astronomers have learned to spot Neptune's storms partly by watching for these companion clouds, the bright flags that announce a dark vortex churning beneath them. The storm tracked since around 2018 has been studied in exactly this way, watched as it drifted and shifted, its bright companion clouds brightening and fading, until at one point it was seen wandering toward the equator and beginning to come apart, as though it had drifted out of the band of atmosphere that gave it life. These are not landmarks waiting patiently for us to map them. They are events, unfolding on a planet that is constantly remaking its own face, and every one we catch is a piece of weather we happen to be lucky enough to see before it erased itself. This was a genuine shock, and it rewrote our understanding of how Neptune works. Neptune's great storms, it turns out, do not behave like Jupiter's. They appear and they vanish on timescales of years rather than centuries. They are born somewhere in the churning atmosphere. They grow into features wider than entire planets. They dominate the face of the world for a few seasons, and then they come apart and fade back into the blue, sometimes within just a handful of years. The planet is constantly erasing and rewriting its own weather. The Neptune you would see this decade is, in a real and literal sense, not wearing the same face it wore the last time anyone looked. Since then, we have caught other dark storms coming and going. Hubble and other telescopes have spotted new dark vortices appearing in Neptune's atmosphere, each one a temporary giant, each one eventually fading. One of the more recent large storms appeared around 2018 and has been tracked ever since, and watching it has taught us something fascinating about how these features behave. Rather than staying fixed, these dark vortices can drift across the planet, wandering through its bands of wind, and in at least one case a storm was observed moving toward the equator and beginning to break apart as though it had drifted into a region where the conditions that sustained it no longer held. They are not landmarks, they are travellers, and they are mortal. The mechanism behind these storms is tied to the structure of Neptune's atmosphere, which is organised into bands of wind moving at different speeds and in different directions, a little like the bands you can see on Jupiter, but with that strange backward dominance we talked about. Where these bands meet, The friction and the differences in speed can spin up a vortex, a rotating pocket of high pressure that sucks the surrounding air into a stable, swirling pattern. For a while, the storm feeds on the energy of the bands around it and holds together. But Neptune's atmosphere is restless, and the balance is delicate, and eventually the conditions shift, the storm loses its grip, and it unwinds. The same processes that build these giants also tear them down. The reason we know any of this, the reason we can talk about storms appearing and vanishing across decades, is a patient and rather beautiful effort to keep at least one eye on the outer planets year after year. For many years now, astronomers have used the Hubble Space Telescope to take an annual portrait of each of the giant planets, building a long-term record of their changing weather. The idea is simple but powerful. By photographing Neptune and the other giants once a year, every year, scientists can watch storms come and go, track how cloud bands shift, and notice slow changes that would be invisible in any single image. It is the difference between a photograph and a time-lapse, between a moment and a story. It was this kind of long-term watching that caught the dark vortex that appeared around 2018 and tracked it as it drifted and faded, and it is this kind of patient monitoring that lets us say with confidence that Neptune's storms are creatures of years, not centuries. But even a yearly photograph from a distant telescope is a thin thread of attention to hang a whole planet on. It can tell us that a storm has appeared or vanished, but not why, not in detail, not the way a spacecraft in orbit could. And between those annual snapshots, the planet is doing things we simply do not see. A storm could be born and die in the gap between two yearly portraits, and we would never know it existed. So even our best efforts to keep watching Neptune leave enormous stretches of its life unobserved, like checking on a restless sleeper once a year and trying to reconstruct their whole night from a single glance. The planet is always ahead of us, always in motion, always rewriting the page just after we have finished reading it. And every time we look closely enough to catch it changing, the same question rises up underneath. Where is all the energy coming from, on a world so far from the sun, to keep building and destroying storms wider than the Earth? Sit with what this means for our knowledge of the planet. The single most recognizable feature of Neptune, the great dark spot, the thing that defined it in every textbook for years, has not existed for more than 3 decades. If you went outside tonight with the most powerful telescope you could find and somehow resolved Neptune's surface, you would not see it. You would see a different planet, with different storms, or perhaps with no great storm at all, just an unbroken field of blue waiting for the next one to be born. Our mental image of Neptune is a photograph of a face that the planet stopped wearing a long time ago. This is the second great clue of the night, and it deepens the unease that the winds first stirred. Neptune is not a fixed object that we simply have not photographed in enough detail. It is a moving, changing, restless world, and the longer we go without watching it closely, the more out of date our picture of it becomes. The winds told us the planet has a hidden source of energy. The vanishing storms tell us that energy is being spent constantly, restlessly, reshaping the world on timescales short enough that a human being could watch it happen. Which brings us, at last, to the obvious and pressing question. If the sun is not powering all of this, then what is? What is the engine buried inside Neptune that keeps this frozen, distant world more alive and more violent than planets sitting far closer to the fire? To answer that, we have to talk about a paradox involving heat, and a comparison with Neptune's nearest sibling that turns everything we expect upside down. Part 5. The heat with no source. Let me ask you a question that seems like it should have an obvious answer. Which is the coldest planet in our solar system? The natural guess, the one that feels like common sense, is Neptune. It is the farthest planet from the Sun, sitting all the way out at 30 astronomical units, receiving 1,000 times less sunlight than Earth. Surely the planet that gets the least warmth from the Sun must be the coldest. It is a perfectly reasonable assumption, and it is wrong. Neptune is not the coldest planet in the solar system. That title belongs to its sibling Uranus, even though Uranus orbits significantly closer to the Sun and receives noticeably more sunlight. That should stop you in your tracks. The closer planet is colder, the farther planet is warmer. Something is badly out of order, and the only way to make sense of it is to accept a startling conclusion. Neptune is not relying on the Sun to stay warm. Neptune radiates considerably more heat out into space than it receives from the Sun, more than twice as much. Some internal source buried far within the planet is generating its own energy, pouring warmth up from below and out into the cold. The sun is barely a contributor. The real furnace is inside. This is the resolution to the puzzle of the winds. Remember, we were left with a contradiction. A world starved of sunlight should be quiet, and yet Neptune drives the fastest, most violent winds anywhere in the solar system. Now we have the answer, at least the shape of it. The engine driving Neptune's storms is not above it, in the form of the distant and feeble sun. The engine is beneath it. The heat rising from the planet's hidden interior is what stirs the atmosphere, what powers the supersonic gales, what builds and destroys the Earth-sized storms. Neptune is a planet warmed from within, a world running on its own internal fire, almost indifferent to the faint star it orbits. Hold on to that phrase, because we are going to need it again before the night is over. The engine is beneath it, not above it. It is the key to Neptune's weather, and as we'll see, it is also tangled up with some of the deepest mysteries the planet still keeps. For now, the obvious next question is what that internal source actually is, and the honest answer is that we're not entirely sure. The leading explanation is that the heat is primordial, left over from the planet's birth. When Neptune formed, more than 4.5 billion years ago, it did so by gathering up an enormous amount of material, and all of that material falling together released gravitational energy as heat. A planet that large cools slowly, and so some of that ancient warmth from its formation could still be leaking out today, billions of years later, like a stone pulled from a fire that stays hot long after the flames are gone. To appreciate how lopsided the energy budget really is, it helps to put a number on it. Neptune radiates roughly 2.5 times more heat than it absorbs from the sun. In other words, for every unit of warmth the distant sun manages to deliver, the planet pours out more than twice as much from its own reserves. That is an extraordinary imbalance for a world we tend to think of as frozen and inert. It means that if the sun were somehow switched off entirely, Neptune's weather would barely notice for a very long time, because the sun was never really running the show in the first place. The furnace is internal, and it is generous, and it has been burning steadily for billions of years. Neptune and Uranus belong to a class of planet that astronomers call ice giants, and that name is worth a moment of explanation, because it is slightly misleading. The ice and ice giant does not mean these worlds are made of solid frozen water like an enormous snowball. It refers to the kinds of materials they formed from, compounds like water and ammonia and methane, which astronomers loosely group together as ices because they would be frozen out in the cold distant region of the early solar system where these planets grew. Inside the planets, those same materials exist as hot, dense fluids, nothing like ice at all. So an ice giant is not a frozen world. It is a world built from the frozen leftovers of the outer solar system, materials that have since been heated and crushed into exotic states. Jupiter and Saturn, by contrast, are gas giants, made overwhelmingly of hydrogen and helium, and they are a different kind of beast. Neptune and Uranus are the smaller, denser, stranger siblings, and they are the least explored major planets in the Sun's family, which makes the discrepancy between them all the more frustrating. Two worlds so alike that they ought to be near twins, and one of them runs hot while the other has gone cold, and the best explanation we have for the difference is a catastrophe we cannot prove. There is something genuinely humbling in admitting that. We are talking about one of the most basic questions you could ask about a planet, the question of why it is warm, and for Neptune the honest answer is that we are not entirely sure. We know the heat is real, because we can measure it streaming off into space. We know it is mostly internal, because the sun is far too feeble at that distance to account for it. We have reasonable ideas about where it comes from: primordial warmth from the planet's formation, energy released by the slow settling of heavy material like those falling diamonds, perhaps some other process we have not fully pinned down. But the exact recipe, the precise balance of these sources, and above all why Neptune has so much of it, while its twin Uranus has almost none, remains genuinely unsettled. This is not a question that was answered long ago and filed away. It is open, right now, today, an unsolved problem about a planet we have known the location of for nearly 2 centuries. And that unsettled energy budget is not just an academic curiosity, because it touches almost everything else about the planet. The internal heat is what drives the winds. It is what powers the storms that appear and vanish. It rises up through that exotic interior of superionic fluid and falling diamond, stirring the whole atmosphere from below. A world with this much internal warmth is not a frozen relic. It is an active, working planet, geologically and meteorologically alive, generating its own weather from its own reserves with barely a nod to the distant sun. When you look at Neptune, you're not looking at a dead ball of ice waiting at the edge of the solar system. You're looking at a furnace wrapped in blue, a self-heated world that has been running its own machinery for billions of years, and whose machinery we're only beginning to understand. To see that machinery, to really grasp what makes Neptune tick, we have to do the one thing no spacecraft will ever physically do. We have to descend, in our imagination, beneath the clouds, down through the screaming winds, into the strange and crushing interior where the real engine of the planet is hidden. But that explanation, satisfying as it sounds, runs straight into a problem, and the problem has a name. Its name is Uranus. Uranus and Neptune are, in many ways, twins. They are nearly the same size, made of broadly similar stuff, both classified as ice giants, a category distinct from the gas giants Jupiter and Saturn. They formed in the same era, in the same outer region of the solar system, from the same kind of material. If primordial heat left over from formation explains Neptune's warmth, then Uranus, its near twin, should be pouring out a similar amount of internal heat. It is not. Uranus leaks almost no internal heat at all. It is, in this one crucial respect, a dead engine where Neptune is a live one. Two planets that should be nearly identical, and one of them is warm from within while the other has gone cold. So what happened to Uranus? Here we step from established fact into careful speculation, and one leading theory is genuinely dramatic. Early in the history of the solar system, when the planets were still young and the spaces between them were crowded with debris, Uranus may have been struck by an enormous object, something perhaps the size of Earth itself. The evidence for this is written into Uranus's orientation. Alone among the planets, Uranus is tipped almost completely onto its side, its axis tilted so far that it essentially rolls around the sun rather than spinning upright like a top. A collision violent enough to knock a planet over like that could also have disrupted the way heat flows out of its interior, in effect slamming the lid on its internal furnace, or letting its primordial warmth escape all at once long ago. Neptune, on this view, was either not struck in the same way, or not as severely, and so its internal warmth survived to drive the storms we see today. That theory is not proven. It is one of the best explanations we have for a genuine and unsolved discrepancy between two worlds that ought to be the same, and it points at something we're going to confront over and over tonight. Even the basic energy budget of Neptune, the simple question of why it is warm at all, is not fully settled. We know the heat is there. We can measure it leaving the planet. We can see what it does to the atmosphere. But the exact balance of where it comes from, why it persists, and why Neptune has it while its twin does not, remains an open question, not a closed one. What is not in doubt is the consequence. Neptune's internal heat means the planet is not a frozen, inert ball waiting passively at the edge of the solar system. It is an active world, geologically and meteorologically alive, driven by forces welling up from a hidden interior. And that interior, when you finally descend into it in your imagination, turns out to be one of the strangest places anywhere in the Sun's family, a realm of crushing pressure and exotic states of matter, where the ordinary rules about solids and liquids break down, and where, if the models are right, it quite literally rains diamonds. That is where we're going next. We're going to leave the screaming winds of the cloud tops behind and sink down layer by layer into the blue toward a core pressed harder than almost anywhere you can imagine. Part 6. Inside the Blue. To understand the inside of Neptune, you have to let go of the idea of a surface. There is no place on Neptune where you could land, no boundary where the sky ends and the ground begins. Instead, as you descend, the atmosphere simply gets thicker and hotter and denser around you, gradually and without any sharp edge, until the gas you started in has become something more like a fluid, and the fluid has become something stranger still. It is a continuous transformation, all the way down, from the thin cold air of the cloud tops to a core squeezed under pressures that defy the imagination. Let us make that descent together, slowly, the way you might sink through dark water, watching the light change as the world above recedes. You begin at the cloud tops, where the temperature is around minus 210 degrees Celsius, and the supersonic winds are tearing past. As you sink, the pale blue light from the distant sun fades quickly and the pressure begins to climb. The thin upper atmosphere of hydrogen and helium and methane grows denser around you, pressing in from all sides. The methane clouds give way to clouds of other compounds, and the temperature, instead of continuing to fall as it would near the surface of a sunlit world, begins to rise because now you are descending toward that hidden internal furnace. The deeper you go, the warmer it gets, and the harder the pressure squeezes. Keep sinking, and the gas around you stops behaving like gas at all. The pressure becomes so immense that hydrogen and the other materials are compressed into a hot, dense fluid, and you pass into the layer that scientists sometimes call Neptune's mantle. It is often described loosely as a water-ammonia ocean, but you must abandon every image that word ocean brings to mind. This is not cool blue water lapping on a shore. It is a scalding, dense, electrically charged fluid of water and ammonia and methane, hotter than the surface of many stars in places, under pressures hundreds of thousands of times greater than the air at Earth's surface. It does not slosh. It does not have waves. It is a thick, churning, conducting medium, and it makes up the great bulk of the planet's mass. Within this layer, the rules of ordinary chemistry start to bend. Some of the water far down in the mantle may exist in a phase called superionic water, a state of matter that almost never occurs naturally on Earth. In superionic water, the oxygen atoms lock into a rigid, solid crystal lattice, while the hydrogen atoms break free and flow through that lattice like a liquid. It is, in a sense, solid and liquid at the same time, a frozen scaffold with a river running through its bones. This bizarre, electrically conductive material, churning and flowing far inside the planet, is one of the best candidates we have for explaining something we have not even gotten to yet. The strange, lopsided magnetic field that Neptune generates, a field that is going to matter enormously when we return to the present and the discoveries of the James Webb Space Telescope. But the most famous thing that happens in Neptune's interior, the detail that captures everyone's imagination, involves the methane. Methane is a simple molecule, one carbon atom bonded to 4 hydrogen atoms. As you descend deeper, the pressure rises toward truly staggering values, building toward roughly 7 million times the atmospheric pressure at Earth's surface near the core. Under that kind of force, the methane molecules are torn apart, and the carbon atoms freed from them are squeezed so hard that they crystallize. Carbon, compressed and crystallized under enormous pressure, becomes diamond. Far inside Neptune, the models suggest there is a steady rain of diamond crystals forming high in the mantle and sinking slowly down through the hot fluid toward the core, perhaps settling into a layer of liquid carbon with solid diamonds drifting within it. Laboratory experiments in recent years, recreating those pressures for fractions of a second, have begun to confirm that this process is physically possible. These experiments are remarkable in their own right, and they are worth picturing. To test whether diamonds really form inside the ice giants, researchers take a sample of a material like plastic, which contains carbon and hydrogen much as methane does, and they hit it with an enormously powerful laser, sending a shockwave through it that briefly recreates the crushing pressure and searing heat found far inside Neptune. For a tiny fraction of a second, in a laboratory on Earth, a sliver of matter is squeezed as hard as the inside of a planet. And in those experiments, tiny diamonds form, exactly as the models of Neptune's interior predict. We cannot send a probe into Neptune's core, and we never will, because nothing we could build would survive the descent. But we can recreate a heartbeat of that environment here, on a workbench, and watch the diamonds appear, and in doing so reach across 4.5 billion kilometers to confirm a rain we will never see fall. There is one more reason the interior matters so much, and it connects directly to a discovery we will return to soon. That churning, electrically conductive layer of fluid far inside Neptune, the so-called water-ammonia ocean with its rivers of superionic water, is almost certainly the source of the planet's magnetic field. On Earth, our magnetic field is generated by the motion of liquid metal in our core, and it is reasonably neat and orderly, roughly aligned with our spin. Neptune's magnetic field is generated by this strange shallow fluid layer instead of a buried metallic core, and the result is a field that is wildly tilted and badly off-center, nothing like the tidy bar magnet we're used to. That detail might sound like an obscure piece of physics, but hold on to it, because it is the key that will unlock one of the most surprising things the James Webb Space Telescope found when it finally turned its attention back to Neptune. The lopsided interior makes a lopsided magnetic field, and the lopsided magnetic field puts Neptune's lights in a place no one expected. Let that picture form fully in your mind. Somewhere below the screaming blue clouds, below the scalding not-quite ocean, In a darkness no light has ever reached and no probe will ever survive, diamonds are falling, not a few, not occasionally. A constant, gentle, endless snowfall of diamond drifting down through thousands of kilometers of crushing fluid toward the center of the world. By mass, Neptune may contain more diamond than any other place in the solar system, and this is not merely a beautiful image. The slow sinking of those dense diamond crystals, releasing gravitational energy as they fall, is one of the proposed contributors to the very internal heat that keeps Neptune warm and its winds blowing. The planet may, in part, be powering its storms by raining jewels into its own core. This is the engine beneath, not above, made vivid. The Sun is a distant star, almost irrelevant to the inner workings of this world. The real action is internal, a hidden machinery of exotic fluids and falling diamonds and primordial heat, turning gravitational and chemical energy into the warmth that rises up and stirs the supersonic sky. It is a self-contained world, lit faintly from outside but driven powerfully from within. One thing that helps when picturing Neptune's interior is to let go of the idea of neat, separate layers with clean boundaries between them. There is no moment as you descend where you cross a line from atmosphere into ocean or from ocean into core. Everything blends gradually into everything else, the gas thickening into fluid, the fluid growing hotter and denser and stranger, the pressure climbing without pause until you reach a central region where the heaviest material has settled. Perhaps a core of rock and metal and ice roughly the size of the Earth, buried at the center of a planet 4 times wider. The mantle of hot, conductive fluid that surrounds that core makes up the great bulk of the planet, thousands upon thousands of kilometers of churning exotic material, and it is in that enormous middle layer that most of Neptune's strangeness lives. The diamond rain forms there. The magnetic field is generated there. The internal heat rises through it. It is less a planet with an interior than an interior with a thin skin of sky. And that is the thing to carry upward with us as we return to the surface and to the present day. The Neptune we see from outside, the blue disk, the bright clouds, the faint rings, the displaced auroras, is only the visible skin of something far larger and far stranger happening underneath. Every storm, every wind, every flicker of light at the top of the atmosphere is an expression of that hidden machinery. The engine beneath, not above. So when the James Webb Space Telescope finally turned back toward Neptune and began to find things no one expected, it was not really discovering new surface features. It was catching fleeting views of how that hidden engine was expressing itself now, in our time, decades after Voyager, on a planet that had quietly kept working all the while. And it is precisely because so much of Neptune's character comes from these hidden internal processes that the planet is so hard to predict and so full of surprises. We cannot see the engine. We can only watch its effects ripple up to the surface, in the winds, in the storms, and in something we still have not discussed, the lights that flicker in Neptune's sky. To see those, and to understand why they shocked the scientists who finally found them, we have to come back up out of the blue, return to the present day, and talk about the new eye we built to look at Neptune again, more than 30 years after Voyager flew past. Part 7. The Rings Nobody Could See. For 33 years after Voyager flew past, our detailed knowledge of Neptune was essentially frozen in 1989. We had the photographs, we had the measurements, we had the great dark spot that no longer existed, and we had the winds and the rings and the moons that Voyager had catalogued in those few hours. Telescopes on Earth and the Hubble Space Telescope in orbit kept an occasional eye on the planet, tracking storms as they came and went, but no instrument could see Neptune the way Voyager had, up close and in fine detail. The planet remained, for all that time, a place we had visited once, and then watched only from a great distance, as a small blue disk. That changed when the James Webb Space Telescope turned its attention to Neptune. Webb is the most powerful space telescope ever built, and it sees the universe in a fundamentally different way than Hubble or the human eye. It is designed to observe in infrared light, the long wavelengths that lie just beyond the red end of what we can see, the light of heat rather than the light of colour. This is not a small technical detail. It is the entire reason Webb could reveal things about Neptune that had been invisible to every instrument that came before, including, in some ways, Voyager itself. When Webb looked at Neptune, with its near-infrared camera, it produced an image that made astronomers catch their breath, and the first thing that leapt out was the rings. Yes, Neptune has rings. Voyager had confirmed them in 1989, but they are faint and delicate, nothing like the brilliant broad bands of Saturn, and they had been extraordinarily difficult to observe in the decades since. In Webb's image, Neptune's rings came into clear focus for the first time since the Voyager flyby. The narrow, bright rings were there, sharp and clean, and so were the planet's fainter, dustier bands, the more diffuse rings that are so dim they had been almost impossible to capture from a distance. To see Neptune's full ring system glowing crisply in a single image, for the first time in more than 3 decades, was a small triumph in its own right, a reminder of how much detail had been hidden simply because we lacked an instrument sensitive enough to pull it out of the dark. But the strangest thing about Webb's portrait of Neptune was the planet itself. In the image, Neptune does not look blue. It looks pale, almost white, a soft and ghostly globe rather than the vivid sapphire we're used to. This is not because Webb got the colour wrong. It is because Webb was not seeing colour at all, in the way we normally mean it. Remember that Neptune's famous blue comes from methane gas, absorbing red light and scattering blue. Webb's near-infrared camera observes in wavelengths from about 0.6 of a micron out to 5 microns, and across much of that infrared range, methane gas is not just absorbing a little light, it is absorbing strongly, swallowing the wavelengths Webb is most sensitive to. So in Webb's eyes, the methane-laden planet appears dim and washed out, a world drained of its familiar colour, because the very gas that paints it blue in visible light makes it go dark in the infrared. There is a quiet lesson in that, one that runs through the whole history of how we have come to know Neptune. The way a thing looks depends entirely on the light you use to see it. To our eyes, tuned to the narrow band of visible colours, Neptune is a brilliant blue jewel. To Webb's infrared eyes, the same planet is a pale ghost with bright clouds floating over a dimmed face. Neither view is more true than the other. They are simply different questions asked of the same world, and each one reveals things the other conceals. The visible blue tells us about the methane in the air. The infrared darkness, paradoxically, lets the high clouds and the faint rings and the warm glow of the upper atmosphere stand out in ways they never could in ordinary light. By choosing to look in the light of heat rather than the light of colour, Webb could see structures and signals that had been hidden from every visible light telescope that came before. This is why building a new kind of eye matters so much, and why Webb did not merely take a prettier picture of Neptune but genuinely expanded what we know. For more than 30 years, our detailed image of Neptune had been frozen because we had no instrument that could improve on Voyager's close-up view. Webb broke that deadlock not by travelling closer, but by seeing in a different light, and in doing so it pulled new truths out of a planet we thought we had already photographed. The rings sharpened, the clouds blazed, and then, when astronomers went beyond the picture and read the detailed fingerprint of the light itself, splitting it apart wavelength by wavelength, the planet gave up a secret it had kept hidden for more than 3 decades. A secret written not in what Neptune looked like, but in the precise colours of the glow at the very top of its sky. And against that pale, dimmed globe, something else stood out brilliantly. High in Neptune's atmosphere at great altitude, there are clouds made of methane ice, frozen crystals riding above the bulk of the absorbing gas. Because these clouds sit so high, they catch the faint sunlight and reflect it back before the methane below can swallow it, and so they blaze in Webb's image as bright streaks and spots against the darker planet, like brushstrokes of light laid across a shadowed canvas. These are the visible signatures of Neptune's restless weather, the high clouds churned up by that internal engine, frozen and gleaming far above the deeper blue. Webb also caught a thin, bright line running around Neptune's equator, which may be a signature of the global pattern of atmospheric circulation, the grand overturning of air that helps drive the planet's winds and storms. In a single photograph, the telescope had captured both the delicate architecture of the rings and the living, moving weather of the atmosphere. It is worth dwelling on what kind of instrument can do this, because Webb is not simply a bigger version of the telescopes that came before. Its main mirror is built from 18 gold-coated segments that unfolded in space like a flower, giving it a light-collecting area far larger than anything previously sent beyond Earth. It sits not in orbit around our planet the way Hubble does, but roughly 1.5 million kilometers away, at a special point in space where it can stare into the dark, kept cold and steady, shielded from the sun's heat by a sun shield the size of a tennis court. All of that engineering exists to do one thing supremely well, to gather faint infrared light from the most distant and the most difficult targets in the universe. And when an instrument built to study galaxies at the dawn of time is turned instead toward a planet in our own solar system, it sees that familiar world with a clarity and a sensitivity that no one had ever brought to bear on it before. Webb did not have to travel to Neptune. It simply had to be good enough from a great distance to pull details out of the dark that everything before it had missed. The image also gathered in Neptune's moons. 7 of the planet's family of moons appeared in the picture, scattered around the bright globe and its rings like a small constellation, each one a world in its own right with its own history. Most of them are small, irregular bodies, but together they hint at the complexity of the Neptune system, a miniature solar system of its own circling the blue giant. And one of those moons, as we have said, outshone everything else in the frame, blazing with reflected light against the methane-dimmed planet. To understand why that moon matters so much, and why it may be the strangest object in the entire Neptune system, we will have to come back to it. But Webb was not done with the planet itself. The portrait of the rings and the clouds was only the first gift. The second was hidden in the light, invisible in any ordinary photograph, waiting to be read out of the spectrum by an instrument sensitive enough to find it, and it solved a mystery that had frustrated astronomers for more than 30 years. There was one more thing in that image, and it nearly outshone the planet. Off to the side, marked with the distinctive spikes of light that Webb's mirror produces around bright objects, was a brilliant point that looked almost like a star. It was not a star. It was Triton, Neptune's largest moon, and it was so bright that it dominated the picture. Triton is covered in frozen nitrogen, a surface so reflective that it bounces back about 70% of the sunlight that reaches it. In the infrared, against the dimmed and methane-darkened face of Neptune, Triton gleamed like a beacon, brighter than the entire planet it orbits. We are going to come back to Triton, because it is one of the most extraordinary worlds in the solar system in its own right, with a story of capture and geysers and a far future fate that is genuinely haunting. But first, Webb was not finished with Neptune. The image of the rings and clouds was only the beginning. Because when astronomers used Webb's instruments to study Neptune more closely, gathering not just pictures but detailed measurements of the light, they found something that had eluded everyone for more than 30 years, something that should have been visible long ago and never was. They found Neptune's auroras glowing in the wrong part of the sky. Part 8. The lights in the wrong place. Auroras are one of the most beautiful phenomena a planet can produce, and we are lucky enough to live on a world that makes them spectacularly. On Earth, we call them the northern and southern lights. They happen when charge particles, mostly streaming out from the sun in the solar wind, are funneled down toward our planet by Earth's magnetic field. That magnetic field is shaped a bit like a bar magnet, with its poles near the geographic poles, and so the incoming particles are channeled toward the far north and the far south, where they crash into the upper atmosphere and make it glow. That is why, on Earth, you have to travel toward the poles to see the aurora. The lights crown the top and bottom of the world, because that is where the magnetic field guides the particles in. Every planet with a magnetic field and an atmosphere should be capable of auroras, and astronomers had long expected Neptune to have them. Voyager 2 had even detected hints of auroral activity during its flyby back in 1989. But actually capturing Neptune's auroras, seeing them clearly and confirming them directly, had stubbornly refused to happen for more than 3 decades. Telescope after telescope, year after year, the auroras of Neptune stayed hidden, a predicted feature that simply would not show itself. It became one of those small, nagging absences in planetary science, a thing that should be there and yet could not be found. In June of 2023, the James Webb Space Telescope gathered the data that finally broke the case, and in March of 2025 the results were shared with the world. Webb had detected Neptune's auroras for the very first time. It did so not by photographing curtains of light the way we see them on Earth, but by using its spectrograph, an instrument that splits light into its component wavelengths and reads the chemical fingerprints written there. In Neptune's upper atmosphere, Webb detected the unmistakable signature of a molecule called the trihydrogen cation, written in chemistry as H3+. This molecule is a kind of universal announcer of auroral activity. It forms when a planet's upper atmosphere is bombarded by charged particles, and it glows in infrared light, exactly the light Webb was built to see. Finding H3+ at Neptune was like finding the smoke that proves there is a fire. The auroras were real, and at last we'd caught them. The scientist who led the work, Henrik Mellin, described the moment with the kind of honesty that makes you understand how much it meant. He said that imaging the auroral activity at Neptune was only possible with Webb's near-infrared sensitivity, and that it was so stunning not just to see the auroras, but to see the detail and clarity of the signature that it genuinely shocked him. After more than 30 years of looking, the lights had finally appeared. It is worth understanding why this particular molecule, the trihydrogen cation, is such a reliable messenger. When charged particles slam into the upper atmosphere of a giant planet, they smash into ordinary hydrogen molecules and knock them apart and rearrange them. And one of the things that forms in the aftermath is this 3-atom ion, H3+. The molecule is, in a sense, a byproduct of the violence of an aurora, created wherever charged particles are pouring energy into the air. And crucially, it glows in infrared light, radiating away some of that energy at very specific wavelengths. So if you can detect the glow of H3+ in a planet's upper atmosphere, you have caught the aurora red-handed, even if you cannot see the curtains of light directly. On Jupiter and Saturn, astronomers had been using this exact fingerprint for years to study auroras. On Uranus too. Only Neptune had withheld it, refusing to show its H3+ year after year, telescope after telescope, until Webb's sensitivity finally teased it out of the dark. And the reason Neptune held out so long turns out to be wrapped up with the second discovery, the one we are building toward. The glow of an aurora depends on the temperature of the gas producing it. A hotter upper atmosphere glows more brightly and is easier to detect, while a colder one fades toward invisibility. If Neptune's upper atmosphere had quietly grown much colder in the decades since Voyager, then its auroras would have dimmed accordingly, retreating below the threshold that earlier instruments could reach. That is exactly what the data suggested. The auroras had been hiding not because they were absent, but because the part of Neptune that produces them had been cooling, growing fainter and harder to see. To find the lights, Webb had to be sensitive enough to catch a glow that had been dimming for a generation, and in measuring that glow, in working out the temperature of the gas, the astronomers stumbled into the most unsettling number of the entire investigation, a number that says the top of Neptune's atmosphere is not the same place Voyager visited at all. But here is the part that turns a triumph into a mystery. On Neptune, the auroras do not crown the poles. They glow at the planet's middle latitudes, far from the top and bottom of the world, in places that, by everything our experience on Earth would suggest, are entirely the wrong part of the sky for an aurora. To understand why, you have to know one more strange fact about Neptune, and it connects all the way back to that exotic, churning, electrically conductive interior we descended through earlier. Neptune's magnetic field is wildly, almost absurdly skewed. Instead of running roughly in line with the planet's spin, like Earth's does, Neptune's magnetic field is tilted by about 47 degrees relative to its rotational axis, and it is not even centered on the middle of the planet. It is offset, shoved off to one side, as though the bar magnet inside Neptune had been knocked askew and then shifted away from the core. With a magnetic field that lopsided, the charged particles are funneled down into the atmosphere not at the poles, but at these odd middle latitudes, and so that is where the auroras burn. Let me put you there one more time, because this is a sight no human eye has ever truly seen, and may not for generations. Imagine you are floating high above Neptune's night side, with the planet a darkened sphere beneath you, and the brilliant point of the distant sun behind. You're not looking toward the poles, the way you would on Earth to catch the northern lights. You're looking at the planet's flanks, its middle, the region that on any sensible world should be dark and quiet. And there, glowing softly in a band that has no business being where it is, are the auroras of Neptune, a faint infrared shimmer painted across the wrong part of the world by a magnetic field tilted nearly halfway onto its side. It is the same phenomenon we cherish in our own skies, the lights born of a planet meeting the wind of its star, but here it is displaced, dislocated, burning in defiance of where our instincts say it should be. Even Neptune's light is in the wrong place. I should be honest with you about what you would and would not actually see, because the reality is in some ways even stranger than a picture suggests. Neptune's auroras, as Webb detected them, glow in infrared light, the light of heat, which human eyes cannot see at all. If you were somehow floating above Neptune looking down with your own eyes, you might not see dramatic curtains of colour the way you would at a good display of the northern lights on Earth. The glow that Webb captured is a signal read by an instrument, a fingerprint in the spectrum, more like a faint warmth detected by a special camera than a blaze of visible colour, and yet it is no less real for being invisible to us. It is a genuine aurora, charged particles pouring energy into the upper atmosphere and making it glow. Exactly the same fundamental process that lights up our own polar skies. It is simply happening in a light we cannot perceive, on a world we cannot reach, in a part of the sky where we did not think to look. That combination, real but invisible, present but undetected for decades, is almost a perfect summary of Neptune itself. The planet is full of things that are genuinely there and yet hidden from us, by distance, by the wrong wavelength of light, by our own assumptions about where things ought to be. The auroras were there all along since before Voyager, glowing faintly at the wrong latitudes in a light our eyes cannot see, waiting for an instrument good enough and a team patient enough to find them. How many other features of this planet are like that, present and real and simply waiting for the right kind of looking? We will never know until we look. And the auroras, remarkable as they are, were not even the most startling thing Webb found in that data. Hidden alongside them was a number that would reveal Neptune to be a planet quietly, profoundly in the middle of changing, and the auroras did not come alone. Buried in the very same Webb data that finally revealed them was another result, an almost accidental measurement that turned out to be the most unsettling discovery of all. To detect the auroras, the scientists had to measure the temperature of Neptune's upper atmosphere, and when they compared what Webb saw to what Voyager had recorded back in 1989, the numbers did not match. They did not even come close. Something had happened to Neptune's upper atmosphere in the decades since our only close visit. Something dramatic, something nobody had predicted, and something we still cannot explain. This is where every thread of the night finally comes together. This is what is moving in Neptune's storms that should not be there. Part 9. The Thing That's Moving. Here is the discovery that gives this whole night its name. When the James Webb Space Telescope measured the temperature of Neptune's upper atmosphere, the region called the thermosphere, and compared it to the temperature Voyager 2 had measured back in 1989, it found that Neptune's upper atmosphere had cooled dramatically, not by a few degrees, by hundreds of degrees. According to the team, the temperature of Neptune's upper atmosphere in 2023 was a little more than half of what it had been in 1989. In the span of a single human generation, between our one and only close visit and the moment we finally looked again with a better eye, one of the most distant planets in the solar system had quietly shed half the heat of its outer atmosphere, and nobody saw it happen. Sit with the strangeness of that. We are not talking about a storm appearing or a cloud drifting. We are talking about the temperature of an entire layer of a planet's atmosphere collapsing to roughly half its former value on a world more than 30 times farther from the sun than we are, in a place where you would expect almost nothing to change quickly, because there is so little sunlight to drive change in the first place, and the cause is unknown. Whether it is driven by long, slow seasonal cycles that play out over Neptune's 165-year orbit, whether it reflects some shift in the planet's internal activity, whether it has to do with changes in the solar wind blowing past, or whether it is something else entirely that we have not even thought of, we do not know. As the scientists themselves put it, the data opens far more questions than it answers. Let us take those possibilities one at a time, because even our best guesses reveal how little we understand. The first idea is seasons. Neptune takes about 165 years to circle the Sun, which means its seasons each last more than 40 years. A child born at the start of one Neptunian season would be middle-aged before it ended. We have been watching the planet closely for only a tiny slice of one of those enormous years, so it is entirely possible that the cooling we measured is just one slow swing of a seasonal pendulum we have never seen complete a full arc. The trouble is that the change seems larger and faster than a gentle seasonal drift should produce, and so the seasons alone may not be enough. The second idea is the Sun's own activity. The Sun goes through cycles of roughly 11 years, growing more and less active, and the stream of charged particles it sends out, the solar wind, waxes and wanes with it. A change in that wind could, in principle, alter how much energy reaches Neptune's upper atmosphere, but Neptune is so far away, and the effect so indirect that it is hard to see how it could drive a change this large. The third idea is that something inside the planet shifted, some change in the internal engine, or the way its energy reaches the top of the atmosphere. And the honest fourth possibility is that the real explanation is something we have not yet imagined. Notice what all of these explanations have in common. Every one of them describes a planet that is dynamic, coupled to forces both inside and outside itself, changing on timescales that we could actually observe if only we kept watching. None of them describes the dead, frozen, unchanging marble that distance once let us imagine, and every one of them was put on the table only because we finally looked again and compared the new measurement to the old one and found that the two did not match. The cooling did not announce itself. It was discovered by accident in the same data that revealed the auroras, by scientists who were not even looking for it. Which makes you wonder, uneasily, how many other changes have swept across Neptune in the decades we spent looking away, changes we will never know about because no one was measuring them at the time. The planet has been keeping a diary that we forgot to read. I want to slow down here, because this is the emotional centre of everything we have talked about tonight, and it deserves to be felt rather than rushed past. We have seen this entire world up close exactly once. One glance, one angle, one moment in time, captured in a few hours in 1989 by a spacecraft that is now drifting silent and dying in the dark beyond the planets. And in the decades since that single glance, Neptune has changed in ways we are only now discovering, and that we cannot explain. An entire planet, large enough to swallow more than 50 Earths, has been transforming itself for an entire human generation, with not a single witness watching closely. The auroras we just found took more than 30 years to catch. The heat that vanished from the upper atmosphere left without anyone noticing until we happened to look again, by accident, while searching for something else. We did not lose a detail. We missed a metamorphosis. There is a particular ache in that, the ache of having looked away from something alive. We tend to imagine the planets as permanent fixtures, fixed and patient, waiting quietly for us to study them whenever we get around to it. Neptune does not wait. It storms and glows and cools and changes, and it has been doing so this entire time, through every year we spent looking elsewhere. If we had kept watching continuously, we might have seen the upper atmosphere cool degree by degree. We might have watched the auroras dim. We might have tracked a dozen great storms being born and dying. Instead, we have 2 data points, separated by 34 years, and an enormous, unwitnessed gap between them, in which the planet quietly became something new. It is a little like returning to a place you knew long ago and finding it utterly transformed, and realizing that the change did not happen all at once, but gradually, continuously, every single day you were away, and that you simply were not there to see any of it. And yet, strangely, this is not only a sad thought, it is also one of the most hopeful ideas in all of astronomy, if you turn it the right way toward the light. It means the universe has not run out of surprises, not even in our own solar system, not even on a world whose address we have known for nearly 200 years. It means there are entire planets within reach of our own sun that can still astonish us completely, that can still make our finest scientists admit openly that the data raises far more questions than it answers. The gap in our watching is not just a loss, it is also a promise, a guarantee that there is still so much left to find, so much still moving in the dark, waiting for us to return and pay attention. This is the answer to the question hiding in the title of tonight's journey. When we say that something is moving in Neptune's storms that should not be there, we're not talking about a spaceship or a creature or a signal. We're talking about something stranger and, in its way, more profound. We're talking about the planet itself, in motion in ways our picture of it cannot account for. Think about everything we have gathered tonight and watch how it all converges on this single point. The winds blow backward against the planet's own rotation for reasons we cannot fully explain. The great storms appear and vanish within years so that the face of the planet is never the same twice. The auroras burn at the wrong latitudes, displaced by a magnetic field tilted nearly halfway onto its side, and now the upper atmosphere has lost half its heat in the time since we last looked closely, and we have no idea why. Every one of these is something moving on Neptune that, by our expectations, should not be doing what it is doing, and every one of them was either discovered or deepened by the simple act of looking again after a long time away. That is the thread that ties the whole planet together. Neptune is not a static object that we have merely failed to photograph in enough detail. It is a dynamic, restless, changing world, and it changes on timescales short enough that a human being could watch it happen, if only we were watching. The cruel truth is that for 34 years between Voyager and Webb, we mostly were not. We took one close look in 1989, and then we turned away, and the planet went on transforming itself in the dark. Let me bring back the phrase we have been carrying all night, because it takes on a new and heavier meaning here. The engine is beneath it, not above it. We first used that idea to explain the heat and the winds, the way Neptune's internal furnace drives its violent weather without much help from the sun. But look at the cooling thermosphere and you see the phrase complicate itself. The internal engine is still down there, still pouring warmth up from below, still powering the storms, and yet the outermost skin of the atmosphere, the thermosphere, has cooled by half, which means something else has a vote too. Perhaps the slow change of the seasons across Neptune's enormous year. Perhaps a shift in how the planet's strange magnetic field channels energy. Perhaps the breath of the distant sun matters more, up there at the very top of the sky, than it does in the depths. The answer is inside the planet, and it is also outside it, and the honest position is that we cannot yet read either one well enough to say. The engine is beneath it, and above it, and around it, and we are only beginning to learn how to listen to any of it. There is an emotional weight to this that I want to name directly, because it is easy to let it slip past as just another fact. We have seen this entire world up close exactly once. One glance, one angle, one moment in time, captured in a few hours in 1989 by a spacecraft that is now drifting silent and dying in the dark beyond the planets. And in the decades since that single glance, Neptune has changed in ways that we are only now discovering and that we cannot explain. An entire planet, 4 times wider than Earth, large enough to contain more than 50 worlds like our own, has been transforming itself for a generation, with not a single witness watching closely. The auroras we just found took more than 30 years to catch. The heat that vanished from the upper atmosphere left without anyone noticing until we happened to look again. We did not lose a detail. We missed a metamorphosis, and that, strangely, is not a sad thought, or at least not only a sad one. It is also one of the most hopeful and humbling ideas in all of astronomy. We are constantly told that we are beginning to understand the universe, that the great questions are being answered, that the map is nearly filled in, and then you turn your attention to a single planet in our own solar system, a planet we found before we ever saw it, a planet we have known the location of for nearly 2 centuries, and you discover that it is still capable of surprising us completely, still doing things we cannot account for, still keeping secrets a few hours' flight from home. For every piece of information we gather about Neptune, the planet seems to offer 3 new mysteries in return. We have not run out of questions, we have barely started asking them, and the planet is not finished with us either, because it has one more resident we have not properly met, a moon so strange that it may be the most extraordinary thing in the entire Neptune system, a captured world on a countdown to its own destruction. Its name is Triton. Part 10. Triton, the Stolen Moon. Of all the worlds that orbit Neptune, and there are at least 14 moons that we knew of when Webb took its portrait, one stands so far apart from the rest that it tells its own complete story. That world is Triton, Neptune's largest moon, and almost everything about it is wrong in a way that turns out to be a clue. The first and biggest clue is the way it moves. Nearly every large moon in the solar system orbits its planet in the same direction the planet spins, going around the same way the planet turns, because that is the natural outcome of forming alongside the planet out of the same disk of material. Triton does not. Triton orbits Neptune backward, in the opposite direction to the planet's rotation, and it does so on a steeply tilted path, inclined at roughly 130 degrees to Neptune's equator. That backward tilted orbit is, to a planetary scientist, a signature as telling as a fingerprint. A moon that formed in place alongside its planet does not orbit backward. The only good way to end up moving like that is to have formed somewhere else and then been captured. Triton, the thinking goes, was not born as Neptune's moon at all. It began its life out in the Kuiper Belt, the wide band of icy worlds beyond Neptune's orbit, the same population of frozen bodies that includes Pluto. Triton is, in essence, a captured dwarf planet, a wanderer from the outer dark that strayed too close to Neptune and was seized by its gravity, trapped forever in a backward orbit that betrays its alien origin. One leading idea for how this happened is genuinely poignant. Triton may once have been part of a pair, a binary system of two icy worlds orbiting each other, and when that pair swung past Neptune, the gravitational encounter flung the companion away into the dark while stealing Triton for itself, breaking up a partnership that had lasted billions of years in a single decisive moment. Triton is not some minor moonlet either, which makes its capture all the more dramatic. It is a substantial world, comparable in size to the dwarf planet Pluto, large enough to have pulled itself into a sphere and to hold onto a thin atmosphere of nitrogen. If it had stayed out in the Kuiper belt where it was born, we would likely talk about Triton the way we talk about Pluto, as one of the significant icy worlds of the outer solar system, a destination in its own right. Instead, fate dragged it into orbit around a giant, and it became a moon, and a deeply strange one. When Voyager photographed its surface, it found terrain unlike anywhere else, including stretches of terrain that scientists nicknamed cantaloupe terrain, because the puckered, dimpled texture looked uncannily like the skin of the melon. We still do not fully understand how that terrain formed. It is yet another puzzle in a system that seems to generate them endlessly. The thin nitrogen atmosphere is part of what makes the geysers possible, and it gives Triton a faint haze and a sky that is not entirely black. But that atmosphere, like everything else here, is precarious and changing. Triton is so cold that its atmosphere is in a constant delicate balance with the frozen nitrogen on its surface, sublimating and refreezing as the faint seasons shift. It is a world running on the thinnest possible margins of energy, a place where a whisper of sunlight is the difference between solid and gas, between stillness and eruption, and all of it, the geysers, the cantaloupe plains, the nitrogen sky, the possible hidden ocean, is riding on an orbit that is slowly, certainly winding down. The very gravitational grip that captured Triton in the first place is still at work, tightening by an imperceptible amount with every pass, drawing the stolen world inexorably toward the planet that took it. Triton's strangeness and Triton's doom come from the same source, and that is perhaps the most haunting thing about it. Whatever the exact mechanism, the result is a moon that does not belong, and that strangeness runs all the way to its surface. When Voyager 2 flew past in 1989, it found Triton to be one of the coldest places ever measured anywhere in the solar system. Its surface temperature sits at around minus 235 degrees Celsius, so cold that nitrogen, the gas that makes up most of the air you're breathing right now, freezes solid on the ground. You would expect a world that cold to be utterly dead, a frozen relic with nothing happening on it at all. And yet, astonishingly, Voyager saw plumes. It saw geysers erupting from Triton's surface, jets of material blasting upward to heights of around 8 kilometers, with their tops sheared sideways by thin, high winds and carried hundreds of kilometers downwind, staining the icy surface in long, dark streaks. Let me set you down there, in your imagination, on the surface of this stolen world. You're standing on a plain of frozen nitrogen, the ground a pale pink and white in the feeble light, harder than rock and colder than almost anywhere you could ever go. The sky above is nearly black, scattered with stars, and dominating it, hanging huge and blue and silent, is Neptune itself, far larger in Triton's sky than the moon ever appears in ours. The sun is a brilliant point, 1,000 times fainter than the one you know, casting a twilight that never becomes day. And then, not far off, the ground splits, and a column of nitrogen gas and dark dust roars silently upward into the thin air, climbing 8 kilometers into the black before its top is caught by a high wind and bent sideways, trailing off across the frozen ground like smoke from a chimney at the end of the world. It is one of the most alien forms of geological activity ever observed, and it is happening on one of the coldest worlds we have ever found, a place that has every right to be dead and somehow is not. What drives those geysers, on a world so cold, is itself a beautiful piece of physics. The likely explanation is a kind of solid greenhouse effect. Sunlight, faint as it is, passes through a translucent layer of frozen nitrogen at the surface and warms the darker material just beneath, and even that tiny amount of warming is enough to turn some of the solid nitrogen below into gas. The gas builds up pressure until it finds a weak point and bursts upward, carrying dust with it, erupting into the sky. It takes only the faintest whisper of sunlight, trapped and concentrated just below the surface, to power these eruptions on a world frozen nearly to absolute stillness, and there is reason to think Triton may hide something even more remarkable beneath its frozen shell. The heat from the decay of radioactive elements in its interior, combined with the gravitational flexing from its capture, may be enough to sustain a layer of liquid water far underground. If that subsurface ocean exists, then Triton joins a small and tantalizing group of worlds, alongside Jupiter's moon Europa, Saturn's moon Enceladus, and Saturn's moon Titan, as places that might, just might, have the conditions for life as we understand it, hidden beneath miles of ice. But Triton's story does not end in the present, and its future is where it becomes genuinely haunting. That backward orbit, the very thing that marks Triton as a captured world, is slowly, inexorably decaying. With each passing orbit, Triton spirals a tiny bit closer to Neptune, drawn inward by the same gravitational forces that captured it. In approximately 3.6 billion years, Triton will cross a boundary called the Roche limit, the distance at which Neptune's gravity becomes strong enough to overpower the Moon's own gravity holding it together. When that happens, Triton will be torn apart, ripped into fragments and spread out into a band of debris encircling the planet. Neptune, billions of years from now, will gain a magnificent new ring system, perhaps one day rivaling the glory of Saturn's, built from the shattered remains of the wanderer it once stole from the dark. A captured world on a countdown to becoming a ring. It is a reminder that even the moons are not permanent here, that everything in the Neptune system is in motion, on timescales short and long, and that the planet we have visited exactly once is changing not only in its storms and its skies, but in the very architecture of its family. Which leaves us with one final question, the question that has been waiting quietly behind everything we have discussed tonight. If Neptune is changing this much, this fast, why have we not gone back? Part 11. A world seen once, changing in the dark. We have spent this whole journey circling a single uncomfortable truth, and now it is time to look straight at it. Everything we know about Neptune in close detail, the winds and the storms and the rings and the moons, very nearly all of it, traces back to a few hours in 1989. One glance, one angle, one moment in time. Voyager 2 swept over the North Pole, drank in what it could, and fell away into the dark, and in the more than 3 decades since, no spacecraft has returned. The James Webb Space Telescope has given us a magnificent new way to study Neptune from a distance, and it has already overturned and deepened our picture of the planet. But Webb is in orbit near Earth, more than 4 billion kilometers from Neptune. It is an extraordinary eye, but it is a distant one. To truly see Neptune again, the way Voyager saw it, we would have to go back, and we have not. The reasons we have not are not sinister, though that has never stopped people from imagining that they are. There is a whole ecosystem of speculation online about Neptune and the outer solar system, theories that we are hiding what is really out there, that the lack of a return mission is suspicious, that the strange behavior of the planet, the backward winds and the vanishing storms, must be evidence of something secret or artificial. It is worth taking those ideas seriously enough to answer them honestly, because the honest answer is more interesting than the conspiracy. There is no hidden mission and no cover-up. There is simply a problem of distance, money and timing, and it is a genuinely hard problem. Start with the timing. Remember that Voyager 2 was only able to reach Neptune because of that rare alignment of the outer planets, the arrangement that lets a single spacecraft slingshot from one giant to the next, and that lines up only about once every 175 years. That window has long since closed. Without it, a mission to Neptune cannot borrow a chain of gravity assists from Jupiter and Saturn and Uranus. It has to be a dedicated voyage, aimed at Neptune and Neptune alone, and even then it faces the brute fact of the distance. A spacecraft needs somewhere in the region of 12 to 13 years simply to make the crossing. That means any Neptune mission is a multi-decade commitment from the moment it's approved. The scientists who launch it may well retire before it arrives. Some of the people who first dreamed it up may not live to see the day to come back. Then there is the cost and the competition for it. Space agencies have limited budgets, and every flagship mission to the outer solar system competes with every other priority, with missions to Mars, with telescopes, with returns to the Moon, with spacecraft to the worlds that are simply easier and faster to reach. For decades, Neptune has lost those competitions, not because it is uninteresting, but because it is so far and so slow and so expensive that other targets keep winning. There is no committed mission to Neptune flying today. There have been proposals, studies and designs, careful plans for orbiters that would finally settle into orbit around the planet instead of flashing past it, but none has yet been funded and built and launched. The most concrete prospect on the horizon comes from China, which has discussed a mission to the Neptune system with a potential launch window around the year 2033. If that mission flies, and if it survives the long crossing, it could one day give us the sustained close-up watch on Neptune that we have lacked for so long. But that is years away from launch, and many more years away from arrival. Scientists have not stopped dreaming about what such a mission could be. For years, planetary researchers have sketched designs for a proper Neptune mission, the kind that would not simply flash past the way Voyager did, but would slow down and settle into orbit, circling the planet for years and watching it the way we have learned to watch Jupiter and Saturn. The most ambitious of these concepts pair an orbiter with an atmospheric probe, a small craft that would plunge into Neptune's clouds and radio back measurements of temperature and pressure and composition as it fell, before being crushed and silenced somewhere in the deepening blue. An orbiter would let us watch the storms form and dissolve in real time instead of guessing from single snapshots. It would let us map the lopsided magnetic field properly, study the displaced auroras up close, watch Triton's geysers erupt, and track the planet's mysterious cooling year by year, instead of comparing measurements taken 3 decades apart. It would turn Neptune from a stranger we photographed once into a world we actually know. The obstacle has never been a lack of interest or imagination. It has been the sheer difficulty of reaching so far, so slow, for so much money, when there are easier and faster targets competing for every dollar. And so, for now, the people who study Neptune do something that requires a particular kind of patience. They squeeze every drop of insight they can out of distant telescopes like Webb, out of the decades-old Voyager data, out of careful modelling and clever laboratory experiments, all while knowing that the answers they most want would require a journey none of them might live to see completed. There is a quiet heroism in that, in devoting a career to a world you will only ever see from a great distance, in laying the groundwork for a mission that someone else, a generation from now, might finally fly. And it sharpens the strange ache at the centre of this whole story, because we are not failing to understand Neptune for lack of trying. We are failing because the universe placed one of its most fascinating worlds just far enough away to stay, for now, mostly out of reach. So for now, we are left in this strange and slightly melancholy position. We have a planet that we know is changing, on timescales we could actually witness, and we are not there to witness it. We caught the auroras only after they had hidden from us for more than 30 years. We discovered the collapse of the upper atmosphere's heat only by accident, by comparing a new measurement to one taken a generation ago. The great dark spot that we put in every textbook stopped existing decades ago, and the planet has grown and dissolved who knows how many storms since, unseen. Every time we manage to look, even from a distance, Neptune shows us that it has moved on without us, that it is a living world running its own processes in the dark, indifferent to whether anyone is watching. There is a particular kind of feeling that comes with this, and I think it is worth sitting in rather than rushing past. It is the feeling of having looked away from something alive. We tend to think of the planets as fixed and eternal, as permanent fixtures we can study at our leisure, as though they will hold still and wait for us. Neptune does not hold still. It storms and glows and cools and changes, and it has been doing so this entire time through every year that we were busy looking elsewhere. The one good look we got is now old enough to be a grandparent, and the planet in that photograph, the one with the Earth-sized dark storm and the particular pattern of clouds, does not exist anymore. We are carrying around a portrait of a stranger, taken once, long ago, and we have been mistaking it for a current likeness. Which raises the last and largest question of the night, the one that turns this from a story about a planet into a story about us, and about the limits of what it really means to know something. We calculated Neptune before we ever saw it. We have known exactly where it is for nearly 2 centuries. So why, after all this time, do we still understand it so little? Part 12. 3 mysteries for every answer. Think back to where we began, to that astonishing night in 1846 when Neptune was found within an hour of looking, less than a degree from where the mathematics said it would be. It was one of the great triumphs of the human mind, a planet conjured out of equations and then located on the first attempt. and it created an impression that has quietly misled us ever since. The impression that to predict where a world is the same as to understand what it is. We calculated Neptune before we ever saw it, and we have been paying for that early confidence in a strange currency ever since, in surprise after surprise, in mystery after mystery, that the planet keeps producing the moment we look closely. Because finding out where Neptune is turned out to be the easy part. The hard part, the part we have barely begun, is understanding what it actually does. There is a kind of humility that only comes from looking closely at something you thought you already knew, and finding that you did not know it at all. We did not predict the supersonic winds, and we still cannot fully explain why they blow backward against the planet's spin on a world starved of sunlight. We did not predict that the great storms would appear and vanish within years, erasing the planet's face and redrawing it again and again. We did not predict diamond rain falling through a not-quite ocean toward a core pressed to 7 million times the pressure of our air. We did not predict that the auroras would burn at the wrong latitudes, displaced by a magnetic field tilted nearly halfway onto its side and shoved off-centre. And we certainly did not predict that the planet's upper atmosphere would shed half its heat in a single human generation, for reasons we cannot name. The equations told us where to point the telescope. They did not begin to tell us what we would find when we looked. There is a strange and fitting epilogue to the story of Neptune's discovery that makes this point better than anything else could. The same mathematician whose calculations found Neptune, Urbain Le Verrier, tried the very same trick again, later in his life, on a different planet. The orbit of Mercury, the innermost planet, also had a small irregularity that Newton's laws could not quite explain, a tiny unexplained drift in its path around the Sun. Le Verrier, fresh from his triumph with Neptune, reasoned exactly as he had before. There must be another hidden planet, he argued, this time orbiting very close to the Sun, inside the orbit of Mercury, tugging on it. He even gave the predicted planet a name. He called it Vulcan. Astronomers searched for Vulcan for decades. They thought more than once that they had glimpsed it. But Vulcan does not exist. It was never there. The same method that had conjured Neptune out of mathematics had now conjured a phantom, a planet that the equations demanded but the universe had never made. The real explanation for Mercury's wandering orbit did not arrive until the early 20th century, and it did not come from finding a missing planet. It came from Albert Einstein, whose theory of general relativity revealed that space and time themselves bend near a massive body like the Sun, and that this bending accounts for Mercury's drift precisely, with no hidden planet required. The lesson could not be sharper. The same confident style of reasoning that had found one world produced a ghost when applied to another, and untangling the difference required not better arithmetic, but a deeper understanding of reality itself. Prediction is powerful, but prediction is not the same as understanding. Knowing where to look is not the same as knowing what you will see. Neptune sits at the very centre of that lesson. We found it by trusting the equations, and the equations were, that time, magnificently right. But finding it was only the beginning of the questions, not the end of them. Nearly 2 centuries later, the planet still drives winds we cannot fully explain, still grows and destroys storms wider than worlds, still burns its displaced auroras and sheds its heat in ways our models did not foresee. The mathematics gave us an address. It did not give us a home, and so the work goes on, patient and unfinished, the slow labour of actually understanding a world we located long ago, a labour that no single equation and no single flyby could ever complete. This is the real lesson of Neptune, and it is a gentle and humbling one to carry into the dark. We live at a moment when we are told, constantly, that the universe is being figured out, that the great map is nearly complete, that the age of discovery is winding down, and then you turn your attention to a single blue world at the edge of our own solar system, a world we have known the address of since before photography existed, and you find that it is still almost entirely unknown to us in any true sense. It still drives the fastest winds we have ever measured for reasons we do not understand. It still grows and destroys storms wider than our whole planet. It still glows with displaced auroras and cools in ways that defy our models. For every single piece of information we manage to gather about Neptune, the planet seems to offer 3 new mysteries in return. There is something almost reassuring in that, if you let yourself feel it the right way. It means the universe has not run out of wonder, not even close, not even in our own backyard. It means there are entire worlds within reach of our own sun that can still astonish us completely, that can still make our experts admit that the data raises far more questions than it answers. It means that the work of understanding, the slow, patient, generational work of looking and measuring and looking again, is nowhere near finished, and that the people who give their lives to it will never run short of things to find. A planet we calculated before we ever saw it, that we have visited exactly once, in a single glance, from a single angle, at a single moment, is still out there turning in the cold, still rewriting its storms and its skies, still keeping its secrets a few hours' flight from home. We will go back someday. Perhaps it will be the mission that launches in the next decade, perhaps one that has not yet been imagined. And when we do, when a spacecraft finally settles into orbit around that blue world and begins the long, patient watch that we have never given it, we will almost certainly find that Neptune has changed again, that the planet we meet is not quite the planet Voyager met, nor the one Webb glimpsed, but a new one, still in motion, still surprising us. Until then, it hangs out there at the edge of everything, a brilliant point of blue light, the last great planet of our sun's family, calculated into existence, and then left mostly alone. In a universe we are constantly being told we are beginning to understand, Neptune quietly insists that we have only just begun. And maybe, as you drift off tonight, that is the most comforting thought of all. There is still so much left to find, so much still moving in the dark, so many answers still waiting patiently 4.5 billion kilometers away for us to come back and look again.